Do you hear me? Yeah, it's perfect. It's a much smaller room, so it's yeah. Okay. Oh, starting in.
Get a pointer, or is it just the analog one?
Yeah, just you take that one. Or we don't really have one. How do you say your last name? I'll probably get it all wrong.
Once again?
Your last name?
No, Strelczyk. Strelczyk.
Strelczyk.
Yes.
Cool.
It's good. Pretty good.
Okay, so welcome to the first of the parallel sessions. Starting a little late, I guess I'll have to adjust appropriately. The first speaker is David Strelczyk, who's going to tell us about measured LBM and how we can increase Reynolds number. Without further ado, I'll pass it back on to you.
Okay, so thank you for the introduction. My name is David Strelczyk. I am a PhD student at University of Wrocław in Poland, under the supervision of Professor Maciej Matyka. And today, as Professor mentioned, I will tell about how to increase Reynolds number in meshless LBM without experiencing additional computational costs. So the motivation for this research comes from the recent work that we have done in our group, which concerns studying fundamental properties of meshless LBM, applying this algorithm to model flows in porous media, and also on a more general research about inertial effects in flows through porous media. So applying meshless LBM to inertial flows is kind of natural way to go now. So meshless LBM in a nutshell now. So we all know standard LBM, which operates on a regular lattice with local collision and exact streaming. Yes, so populations placed in one node during the streaming step get advected exactly to one of its neighbors. Now, meshless LBM is capable of operating on scattered discretizations of non-connected nodes with collision step performed the same way as in the standard LBM locally. However, during the streaming step, the departure nodes of the populations usually do not coincide with the discretization points. That's why prior to streaming, we need to interpolate the populations from the discretization nodes to the virtual now departure nodes, and only then stream them to the target discretization nodes. In this way, we achieve the decoupling of space and velocity discretization. In the results that I'm going to show today, we use radial basis functions generated finite differences for meshless approximation, which is implemented in Medusa library, and Lagrange interpolation whenever nodes are arranged on a regular lattice. Now a quick reminder how to increase Reynolds number in standard LBM. So one has three options to choose from: either decrease viscosity, increase reference velocity of the problem, or increase the reference size of the problem. Out of those, only the last option brings no threat of introducing instability or violating stability conditions in the simulation, but it means inserting more nodes into the domain, so it makes the simulation more computationally costly. At the same time, decreasing the lattice parameter means decreasing velocity and space errors simultaneously. It is often the case, however, that space errors does not need decreasing in certain parts of the domain or in the whole domain. So it is desirable to have an algorithm to control those two types of errors separately, and meshless LBM, due to the decoupled space and velocity discretizations, is such an algorithm. So now, how to increase Reynolds number in meshless LBM? So in contrast to standard formulation, where decreasing streaming distance means decreasing the lattice parameter or space discretization parameter at the same time, With the coupled discretizations, we have the whole space spanned by those two parameters free to explore. So for example, to increase reference size of the problem in meshless LBM, we can keep the positions of the discretization points intact while we decrease the streaming step. In this way, some reference length of the problem, let's say the distance between this point and this point, is represented by more lattice sites. Equivalently, we can keep the streaming distance intact and scale only the positions of the discretization points. So this approach to changing Reynolds number in interpolation supplemented LBM in general was presented by He and others in 1997 paper. And we extend their work in several ways now. We apply this Reynolds number scaling procedure to scattered discretizations with meshless approximation. We consider problems with more complex boundary shapes, and we make timing comparison with standard LBM. So the hypothesis we're going to address in this study are the following: that the Reynolds number scaling is possible in meshless LBM, that this scaling is limited by increasing space errors, and that meshless LBM can run faster than standard LBM at the same Reynolds number. As a general validation of the meshless scheme, we performed two tests, lid-driven cavity and porous medium flow. So in the first case, we were able to accurately reproduce velocity profiles along center lines for Reynolds numbers ranging from 100 to 3200. When we wanted to increase Reynolds number even higher, which meant scaling the domain even more, we needed to increase the approximation order and the number of stencil neighbors in meshless approximation. Concerning the porous medium flow, we captured the onset of inertia against Reynolds number, which is represented by the share of kinetic energy confined in the vortices. However, here, increasing the approximation order and the stencil size did not grant reaching the higher Reynolds number. Let us now go on to the efficiency study. So the benchmark test here is the Karman vortex street, and the reference solution at Reynolds number 84 is the standard LBM. To achieve higher Reynolds number, we used meshless LBM, and we did so up until twice the Reynolds number for the reference case. The meshless LBM used scattered discretization near the cylinder and in its wake, and the regular nodes placement away from the cylinder. I note here that although the nodes in the bulk are placed regularly here, we still use interpolated streaming because of the difference of the streaming distance and the discretization parameter. The density of nodes was taken to be the same as in the reference LBM near the cylinder and was made coarser away from the cylinder. So in the scattered part, we used meshless approximation, and in the regular part, we used Lagrange interpolation. Inlet velocity was chosen to be the same as in the reference LBM setup. However, due to numerical instabilities, we needed to increase the viscosity a little bit. And the Reynolds number scaling was, of course, achieved by decreasing the value of the streaming distance. So as a validation of this test, we considered Reynolds number dependence of the Struhel number, which is non-dimensionalized vortex shedding frequency. And you can see that the meshless LBM results, dark dots, fall within the ranges reported by experimental studies previously. Let us now move to the comparison of CPU times between meshless and standard formulation. So we consider the execution time needed to perform or to simulate 1 second of vortex shedding versus Reynolds number. So both algorithms need more time to simulate higher Reynolds number. And this is because while we decrease the streaming distance due to the diffusive scaling, we decrease also the time step length. So we need more time steps to be executed to reach 1 second inside the simulation. However, the slope of the increase is different for meshless LBM and for the standard LBM. This is because in standard LBM, not only the number of time step increases, but also the number of nodes increases when we decrease the streaming step. For the highest Reynolds number considered, meshless LBM performed about 3 times quicker than the standard formulation. So finally, let me go to why meshless LBM performs faster than standard LBM. And to address this question, we'll consider the CPU time needed to perform 1,000 iterations, regardless of the time step length. We'll compare the LBM solution with the reference setup for the lowest Reynolds number and solutions obtained for higher Reynolds numbers via scaling of the domain with 3 meshless LBM scenarios. The first scenario consists of scattered discretization in the whole domain, so also meshless approximation in the whole domain, with the nodes density the same as in the reference LBM solution for the lowest Reynolds number. In the second scenario, we trade the scattered discretization away from the cylinder to a regular discretization, and we keep the uniform density unchanged. In the third scenario, we additionally coarsen the discretization away from the cylinder and its wake, and this discretization is actually the one used for the Strual number calculations presented earlier. So 3 observations from this plot. First is that standard LBM needs more computation time as Reynolds number increases due to the reasons mentioned previously. Second is that for each meshless scenario, the execution time stays unchanged across the Reynolds number because while we change only the value of the streaming step in meshless LBM, we do not insert more nodes into the domain. So in this sense, the Reynolds number scaling in meshless LBM is indeed constant. Third observation is that about 60% speed up between scenario 1 and 2 was achieved solely by changing the arrangement of the nodes in the bulk and the approximation scheme from meshless to Lagrangian in the bulk, although the number of nodes actually increased between those 2 scenarios. Further speed up between scenarios 2 and 3 was achieved by appropriately choosing the nodes density explicitly by making the discretization coarser where coarser discretization was sufficient. So to sum the things up, we showed that costless Reynolds number scaling is possible in meshless LBM, that the maximal achievable Reynolds number at a given space discretization is limited by the space approximation errors, that careful choice of the approximation scheme, nodes layout, and nodes density can make meshless LBM perform faster than the standard LBM. All these results provide further motivation for research on meshless LBM, and things that I've shown you today are available with more detailed description in our archive preprint from the last year. Also, those results and the results from all my PhD studies will be made publicly available at the end of this year in my PhD thesis. And finally, I would like to acknowledge the financial support of Polish National Science Center. So, thank you.
So thank you very much for this presentation. Considering that you are not anymore restricted to lattice, you could consider adaptive refinement throughout the simulation. Would that be feasible though? Because wouldn't you, did you consider this, or would it be infeasible anyway because you recalculate the RBF parameters ways?
Well, you would need to recalculate RBF parameters. You would need to interpolate the distribution functions to the new nodes. But this is something that is common procedure in meshless community. So in this study, this was arbitrary refinement because we know more or less the solution to the problem, but nothing stands in the way of performing adaptive refinement on fly. To initialize, well, the most computationally demanding part is to compute the weights because this involves matrix inversion. So this is directly connected to the number of stencil neighbors that you consider for the interpolation. In this case, we use 25 neighbors, so we need to invert 25 by 25 matrices, right? In general, for meshless approximation on scattered nodes, you might want to use more stencil members than on a regular lattice. Yes, because of the non-aligned nodes position. So in those simulations, it takes several seconds, yes, for how many? 100,000 nodes to initialize the simulation. And you would need to do a part of this job every time you refine the discretization on fly, right?
So in the previous slide, you reported the performance comparison for execution time per 1,000 time steps. But if I understood correctly, you have to change the time step in your methods to get to higher latency numbers. So I'm wondering how this graph would look if you would look at the execution time per physical time.
Oh, this would look like this. Yeah, so this is execution time per 1 second of in simulation time. Yes. So the most prominent observation from here is that the slope of the dependence is higher for standard LBM than for meshless LBM. Yeah. And of course, I didn't show here all those 3 scenarios, just the bottommost one. Yeah, so those. No, I think that those 2 uniformly placed of uniform density would be, of course, higher than the presented meshless results here, right?
Usually the LBM performance limited by the memory bandwidth, right?
Mm-hmm.
But now you do a lot of manipulation. Are you still limited by bandwidth, or are you computationally?
Well, the reading of the weights, reading of the values of the function to be interpolated is a known bottleneck in meshless methods, especially when you switch to GPU. Yes, so you need to read it back and forth. So we didn't do any optimization here in either of the methods, but you can speed up the performance by properly laying out the data in the memory. Yes, so that's for a given chunk of the domain, you read the coefficients and interpolate the values only once. You don't jump between nodes which are not spatially close to each other.
But that's right now you don't really have the consecutive memory accesses.
No, in a way, there is some pattern in the nodes placement because the space filling algorithm proceeds kind of like marching front. Yes, so it goes like spiraling from the boundary down to the center of the domain. But I believe that much better memory layouts is possible here. Yes.
Okay, let's thank David again.
Thank you.
So now we have a presentation by Oliver Kulak, who will tell us about another model for electrical model for electrodynamics. So without further ado, who's on here?
Thank you for the kind introduction, and thanks to the organizers for making this happen here in Zurich. So we are a group of solid mechanics people, so our motivation is to use lattice Boltzmann for problems in solid mechanics. Previously, we were working on lattice Boltzmann for elastostatics, so in the quasi-static limit. And now we focus on the dynamic case where we actually expect more competitive performance of lattice Boltzmann because of the inherent time dependence of the method. This is a joint work involving Martin Geier from TU Braunschweig and my PhD supervisor here at ETH. So, of course, I don't need to motivate that lattice Boltzmann is a powerful method in fluid mechanics. For us, being solid mechanics people, we naturally asked ourselves the question, can we use the computational benefits of the method for solving problems in solid mechanics? And here, first, we just isolate the solid domain itself, but then the overall end goal would be to be able to solve fluid-solid or fluid structure interaction problems in a single framework, here being LBM. The idea is not completely new. There have been, where's the stick? There it is, yeah. So there have been works already dating back more than 20 years ago, which started with some quantitative or no more qualitative examples of how this could look like. And then recently, we also added something here, at least for the elastostatics case. But for the elastodynamics case, at least to our knowledge, there hasn't been a method that demonstrated second-order consistency and also supplied rigorous stability estimates. So that's something we try to do with this project here. Let's briefly outline my talk. So I will introduce the problem of linear elastodynamics. Mostly you're fluid mechanics people, I guess, so I will motivate the equations here. Then it will turn out to be very helpful to reformulate our target equation as a linear first-order hyperbolic system of equations, for which then in a very straightforward way, we can propose a vectorial lattice Boltzmann formulation. Having this, then we will assess consistency and stability of the method, and I will conclude with some numerical verification examples. Our target equation here, so first I will introduce the periodic problem. So the equation comes from Cauchy momentum balance. So we have balance of linear momentum, and we have here our primary solution quantity being this vector u here. As opposed to Navier-Stokes equations, this is not the velocity field, this is a displacement field. So how far our material points displaced from its reference configuration. Then we have the constants of material density rho, and then we have two material parameters here for linear elasticity being the shear and bulk modulus, which sort of give us a resistance towards volumetric and shape-changing deformation. So there's a different kind of resistance of our material. And then we have B bar, which is some external source term. You can think of maybe a distributed load, for example, gravity or a magnetic field or something else. And here we limit ourselves to the case in 2D. And for the periodic problem, we assume that our solution is periodic in space on a square domain, so that we only need to solve the problem on a cutout domain. Of course, we need initial conditions here for the displacement and the velocity also. Then all the examples later I will show for the Dirichlet problem. So we also already have Dirichlet type boundary formulations for the lattice Boltzmann method, where instead of the periodicity, we have a bounded domain, and on the domain boundary, we supply the displacement on the boundary. Okay, starting from this target equation here, we introduce a few intermediate quantities. First thing is we assume a Cartesian reference frame with the unit basis vectors Ex and Ey, and then we express all of our vectorial quantities with respect to this basis. So we have the scalar components Ux, Uy being the displacement components in the respective directions. The same then here, for example, for the velocity and also for our source term. And then also here, dividing the material parameters, shear and bulk modulus by the density, we get these speeds here, Ck and C mu. And then we also introduce some other quantities, these Js, Jd, Jxy, which are sort of precursors of the Cauchy stress solution. It's not quite the Cauchy stress, but they will appear here then in this canonical form of our first order hyperbolic system. So we bring this target equation into this form. It's the same equation, just written in a different way. But this allows us, so now we only have a first time derivative here, and then we have this standard form of a hyperbolic system of equations. And then here we plug in all these definitions. So if you introduce all these equations into each other, you get back to the equation we started with. The good thing is, if we use this equation here, the connection has been drawn a long time ago by Paul Deller, that you can then again reformulate this equation as this Jin-Xing type relaxation system, for which Lattice-Boltzmann is a very natural and very simple discretization method of it. So for this, we do Lattice-Boltzmann, vectorial Lattice-Boltzmann, where, as always, we have this uniform lattice here. So we tile our space with a uniform grid size and put the nodes in there. The same with the time. And we also introduce a velocity set here. We use a 2-index notation in 2D, where I and j just denote the unit velocity component in each of the directions. And then here, this v then is our set of indices for all the velocities we consider here. So you can already see we only need 4 microscopic velocities, only 4 populations. The big difference with respect to conventional Lattice-Boltzmann is that now our populations are vector-valued quantities, not anymore scalar quantities. Here it's 5, because on the previous slide, our hyperbolic system was having 5 equations. It could be, of course, an arbitrary and a natural number of components here. And then the same thing as with normal Lattice-Boltzmann, we have streaming and we have collision, where here this B is then our external forcing that we also apply here in this case. For the case, so this is, I would say, just a general outline of vectorial Lattice-Boltzmann. In order to solve the equations we want to solve, so this hyperbolic system of equations, we need to supply here this first order equilibrium. Maybe remember this hyperbolic system we were looking at on the previous slide was the linear problem. So we get away with the linear equilibrium function. And we define our numerical approximation of the primary solution vector here as follows with we identified with the 0th order moment plus half the forcing. So then the big question is this consistent, and is it second order consistent, and also is it stable? So I will go into this. So actually, it's not yet published, but hopefully soon. We analyzed the consistency of the method using asymptotic analysis. And for this, we just list a few assumptions that we require in order to establish second order consistency for the method. Here, the analysis is done for a periodic domain, but also later, I won't show this in this talk for sake of time. We have formulations for Dirichlet type boundary conditions for which the same statements hold as well. So the first thing being the first assumption, we are on this D2Q4 superscript 5 velocity set. So we have 4 populations, and each of the populations is a vector-valued quantity with 5 components. Our 0th order moment we identify with the primary solution vector, this capital U of our hyperbolic system of equations. Then we have this linear equilibrium type expression. We assume acoustic scaling in the analysis, and we need to supply 0 dissipation. So this is something fairly well known, I would say, that for hyperbolic equations, if we have dissipation in there, of course, we do not recover the non-dissipative behavior of the equation we want to solve. So we need to put our relaxation rate to 2, which is, of course, a very delicate thing with Lattice-Boltzmann. But later, more on this in the stability analysis. Then doing asymptotic expansion here. So we assume a certain polynomial ansatz for our populations here in the smallest parameter of the time step size. We introduce this in our Lattice-Boltzmann equation, perform the Taylor expansion and so on, and then we can see at different orders of the smallest parameter what kind of equations our primary solution or our numerical approximation is solving. So here, if we carry out this, so of course we have the same expansion here for our 0th order moment here, because it's just a linear combination of the populations. We see here that the leading order expansion coefficient indeed solves our equation, our target equation, which is good news. And then if we look at the next higher order expansion coefficient, it is also a solution of a PDE, which is almost the same as the PDE we want to solve without any source term. How can we make sure that this U1 is 0 so that we have second order consistency? I think for this problem, it's fairly straightforward to see. We need to supply 0 initial conditions. And if there are boundaries present, the boundary conditions need to be homogeneous at the leading order. Otherwise, there's no chance that we have a homogeneous solution there. But if we satisfy these conditions, we have second order consistency. Okay, stability. On the slide before, I already said we need to put 0 dissipation, which is a very delicate thing with lattice Boltzmann. So we actually put quite some effort into establishing rigorous stability estimates, even in the case of 0 dissipation. For this, we use the notion of these so-called pre-stability structures. It's already a fairly old idea, but I feel like it's never really fully been picked up in the lattice Boltzmann community. But here, for our case, it was really helpful. So the first thing is we take all our vector valued populations, we put it in a big vector of vectors, and then we can write the collision operation as this compact notation here. We just take the pre-collision vector of populations, apply this matrix here, some identity plus J, and get post-collision. So this is a very compact notation of the collision operator here. And then the question is, how can we make sure that this matrix representation of the collision operation gives us a stable scheme? So for this, here I just print down the statement taken from these works here. This matrix J, which represents our collision operator, admits a so-called pre-stability structure if there exists a matrix P with these 2 properties, so that there exists a similarity transform, so a diagonalization of our J matrix, and that this P transpose P itself forms a block diagonal matrix with positive definite symmetric blocks. If we have such a P, we can define a weighted L2 grid norm. So we sum over all lattice nodes. We weight our population vector here with this matrix. And we can also write this, we can decompose this using this property here. So instead of applying the capital P to the whole vector of populations, we can take the individual populations and compute these weighted L2 norm products. So of course, I'm skipping here many steps, but in the case of without forcing and for periodic boundary conditions, we have an extension of this proof for the case with boundary conditions as well. I'm not talking about this here. We can show indeed that for each arbitrary time step, the value pre-collision here at the current time step is greater equal post-collision, which is the same after streaming. So we see that at each time step, the population vector, the weighted L2 grid norm, does not increase. So that's good for us. That's a sufficient condition for stability, I would say. One thing we can actually show, so this holds for omega between 0 and 2, and this extra condition here. So we have here again these speeds here, C mu, CK, and our lattice speed. This is a standard CFL condition. So this holds only under the condition that we satisfy this CFL type condition, so that the physical propagation speed of information is smaller than the numerical propagation speed of information. And actually, it turns out that if we set omega equal to 2, this turns into an equality. So our collision and streaming is an isometric operation. Okay, I don't have much time left, so we'll just very briefly go over some numerical experiments here. For consistency, we carry out convergence studies using manufactured solutions. So we just assume you're a certain solution of a certain form. If you want to see how this looks like, so this is how the solution looks like on the top here. So this is the norm of the displacement field, and then here's a comparison of the exact solution and the numerical approximation. Looks fairly well. And then, of course, the more rigorous result here is actually, if we go from right to left, we go from coarse to finer meshes. How does the error evolve? So this is done here in the L2 norm, L infinity norm for the displacement, and here L2 norm, L infinity norm for the stress. You can see here it's always second order convergence, also here, but not here. This is an effect of Dirichlet type boundary conditions. So you can see here L infinity norm, this is an extremely sensitive measure, because if something goes wrong somewhere in the domain, it immediately picks this up. And from this, we can actually see that this, we observed this behavior previously with other boundary conditions. This is an effect isolated to the boundaries. There's something going wrong at second order, but it's isolated to the boundaries. That's why we have second order in the L2 norm still, which is good enough for us. Stability, I told you that if we satisfy the CFL-like condition, the weighted L2 grid norm stays the same over whatever time steps we do. So here we just initialize our problem with a certain solution and let it run. And then we see actually that here, for this given simulation, we see that up to machine precision, we conserve the value of this weighted L2 grid norm. Then also we did another experiment, again with a manufactured solution. See here, the final time is quite large. So we let it run for really long times. It's actually 1 million iterations. We do this once for a parameterization where we expect stable behavior, another where we expect unstable behavior. You see for the unstable, it blows up immediately after about 100 time steps. The other one stays stable for really long. All right, to sum up, so we have a new lattice-Boltzmann formulation for linear elastodynamics using vectorial lattice-Boltzmann. We have second order convergence and we have rigorous stability estimates. I didn't talk about initial conditions and Dirichlet boundary conditions, but this works as well for these cases. Okay, thanks. I'm open for questions.
Yeah, so would it change the picture a lot if you allowed for beyond Cookian regime? Or is it already implemented?
You mean more, I see. It would change, but the framework we have here, I'm quite confident can deal with this. Yeah. Maybe the stability might be a bit more challenging to establish then. Because here everything is linear, so we get really sharp results, which then might be more difficult to achieve.
Linearity in coefficients, I guess.
We didn't do it yet, no.
Then I'm trying to get a sense of what your statistics mean in terms of physical materials. So say I have a piece of rubber, what does delta X mean? What does delta T mean? And when you say you can simulate like 10 to the 6 time steps, how much is that actually?
Good question. Actually, I don't know. No.
Because you know the basically the weight rotation.
Yes. Yes. Yeah. Yeah. So it's the same bound as for standard explicit dynamic simulations. It's not better and worse. Yeah.
Okay, they are too much for lunch. We should probably stop it here and thank you. And our next speaker is Paul Zeller, who already gave a brief preview. Thank you. Sort of earlier just coming now to the tolerant. So we'll be talking about a novel way of looking at electrodynamics within electrons.
Actually, I have no idea how this goes on.
They're just on your ears.
I need to shout like it.
Oh, I'm doing it wrong, of course. Second,
You want to have your hand in front?
Okay.
Don't pull
Yeah.
it on something like this.
Okay.
no,
Are you sure I can't just shout?
all right.
Okay, right.
There we go.
Yeah.
Well, take it away.
Okay, thank you. So this is had a quick unexpected advert when Ilya was asking for adverts. So I'm going to talk about lattice-Boltzmann formulations for magnetohydrodynamics, which involves Maxwell's equations, magnetic fields. It's about how you preserve the condition for Maxwell's equations that says that the divergence of the magnetic field ought to be 0, whether we can do that numerically, and then how we can repair things when we find that typically that doesn't hold exactly in a discrete system. So then various structural things in the MHD equations break, and it's different ways to repair them. And I'm going to talk about implementing Powell's 8-way formulation by putting various terms involving the divergence of the magnetic field into the collision operator in order to do repair work. And then, okay, so MHD, single fluid description. So unlike, say, Patrick Jenny's talk this morning, we're just going to have a single fluid which has got 2 kinds of charges. We're not going to resolve different species. And you can use this for astrophysics, space weather, liquid metals, fusion, etc. So we start with Maxwell's equations, which in principle have electromagnetic waves and the speed of light in them. But if we're looking at phenomena which moves fluids moving slowly compared to the speed of light, we can ditch that term. So now the E electric field is just kind of a flux that lives in here for evolving the magnetic field, which should be divergence-free, and we've got rid of Maxwell's displacement current, so the current is now just the curl of B in some sensible units to get rid of the constants. So then the simplest way to specify this flux is Ohm's law, which says the electric field in the frame moving with the fluid is just some constant resistivity I call eta times the current. So I put that in here, I get an evolution equation for the magnetic field. It's advected and diffused like a vector field, and the magnetic field in turn exerts a force on the fluid, this Lorentz force here, J cross B in the momentum equation, which we can also write as the divergence of a thing called the Maxwell stress. But spoiler alert, this is only true when div B is 0. So if I do vector calculus on this, I get that provided the divergence of B is 0. Yeah, so Maxwell's equation says that should stay true if it starts true, because if we take our evolution equation for B, take its divergence, time derivative of the divergence is the divergence of the curl, it's identically 0. So that should be true exactly in real calculus, but it's easy to break that. And if you break it in particular, you can no longer write the Lorentz force as the divergence of a thing, so momentum conservation immediately has a problem. So there are 3 main ways that you can try and fix this numerically. One is you can pick a discretization so that discrete with a twiddle's divergence of the discrete of a twiddle's curl is still identically 0. And I've recently found that a particular kind of magic 2 relaxation time lattice-Boltzmann scheme has this property, so that this holds exactly. If you start off with a discretely divergent magnetic field, it stays discretely divergence-free. Another thing that people have done is to say, well, we could just project B onto divergence-free vector fields every time step. So again, like Patrick Jenny was talking this morning, that you repaired the energy and the momentum conservation, we could repair this condition, but that's very expensive because you typically need to solve an elliptic equation to do that projection. So the third variant is that we repair or extend Maxwell's equations so that they can accommodate this thing not being non-zero. And then it's natural to say, well, we need another magnetic current here to go with the magnetic charge. And then this system is invariant under rotations that mix up the electric and magnetic fields, whereas real Maxwell is distinguished because we have a source term in the DTE term and a source term in the DV terms, but normally no matching sources in the B terms. Then having magicked these things up, we have to pick what are we going to do with them. So one way, and this is something that Philip Hillary has worked on in a lattice-Boltzmann context, is we say, let's put in a gradient of a scalar here. You could imagine this is like doing a general Helmholtz decomposition of any old time derivative of B into a curl of a vector and the gradient of the scalar. And then it turns out that lattice-Boltzmann MHD, in my formulation, sort of does this anyway, but the equivalent time scale is so short, you can't really see it. Another variant that was earlier is to say, well, okay, let's make magnetic charges, say, advect with the fluid velocity u to make a magnetic current. So this restores Galilean invariance to the MHD equations even when div B is not 0. And if you look at the Riemann problem, for a hyperbolic system, there's a new wave to do with the divergence of B, which is why this gets called the H-wave formulation. If we're doing lattice-Boltzmann things, so they've got finite resistivity, finite viscosity, it's more natural to extend this. So instead of this would be natural for ideal MHD, we introduce a little bit of diffusion of charge. So there's a U times a thing and a gradient. To match Ohm's law, we've got a U times a thing and a gradient. So then if I pop these two lines into my extended Maxwell's equations, I get this evolution equation. This is standard ideal MHD so far. This bit says that magnetic charges get advected by the fluid and they diffuse. And then, so I take the divergence of this thing. New term here says magnetic charges get advected and they get diffused. Whereas in Maxwell's equations, they would just sit there and do nothing, and we'll see that later. Okay, implementation details. So putting the Maxwell stress in the lattice-Boltzmann formulation is easy. You just change the second moment of the equilibrium. So you've already got gas pressure, this Galilean Reynolds stress kind of term, magnetic pressure, magnetic tension. That's easy. So I want to think about how I get a discretized. I like to discretize by Strang splitting. So I take my discrete Boltzmann PDE with a quite general collision operator. Say I want something that's second order accurate. So I can't just do stream collide because those steps don't commute and they give me a splitting error. So instead I do half a collide, a stream, half a collide, and that's exactly the same as regular lattice Boltzmann collide, stream. If I do this half a time step of collisions to transform from the Fs to some things I call F bar, and it's easiest to do the collisions on the moments and then convert to the Fs. So that's kind of technology. Okay, to do the induction equation, the problem is momentum equation, first moment of a scalar distribution function, take a moment, I get divergence of a symmetric stress tensor. This thing has to be symmetric by construction, which is great for angular momentum conservation. You can't do MHD like this because I want something like this with an anti-symmetric tensor that's pretending to be the curl of a vector. So I'm going to promote my distribution functions, as Oliver was talking about just a few minutes ago, to be vectors. They're now in bold. My magnetic field is the 0th moment of these vectors. Equilibrium, 0th moment of that's the same vector. So if I take the 0th moment of this equation, I get my pretend Maxwell equation, this thing with the first moment that in turn involves according to the second moment. This is the usual stuff so far. And then if I do a multiple scales expansion on those moments, at leading order, I pick this to be the anti-symmetric product of U and B. So I get ideal MHD at leading order, first correction, turn the usual Chapman-Enskog handle. I find my first correction is the gradient of the magnetic field. And you say, hang on a minute, that's not symmetric or anti-symmetric. And that's where I get this Laplacian coming in through. And something that we're going to need later is that I think this thing's falling off. Too big. Right, thank you. What we're going to need later is that the trace of this thing is 0, and so the trace of the whole lambda thing is a good consistent proxy for divergence of the magnetic field. And lattices in 2D, I have 5 velocity lattice, 2 copies for the magnetic field, 1 9 velocity lattice for the fluid. In 3D, D2Q7, I can have a basis of moments using my B, my lambda, and the parts of the M that don't vanish identically on this lattice, so I can collide in moments, reconstruct distributions. You get me speed up. Okay, so just an oldish picture now, regular MHD, some big simulations for the time were done using this algorithm, so it's not just a sort of a toy for theorists. So now I want to do that 8-wave version, so I need to put in new terms in the momentum equation, possibly, and the induction equation that depend on Dsfd. And if I do that, that implies new terms. So I think we're quite familiar with this in the lattice-Boltzmann business, where if you put in a body force, you need to change the evolution equation of the stress to match, so that when you compute the deviatoric stress, it doesn't get contaminated with the body force. You need to do the same thing that this lambda tensor doesn't get contaminated with source terms. This looks a horrible mess, but there's a very nice way to do it. Basically, moments of Cooper-Stokes exact difference method, which says what you do is you form the non-equilibrium momentum flux, you collide, and then you add on the equilibrium with the new velocity, and that automatically puts in the source terms. And similarly with the electric field, I form the non-equilibrium part, I collide, I rebuild with the new equilibrium electric field, and that automatically incorporates all these horrible source terms. It's very neat. So I worked it all out from first principles, and it boils down to this. Very neat. So the simplest variant says, let's leave the momentum equation alone. So we keep momentum conservation. We put a Dsfd term in the induction equation, which becomes a trace lambda term, discretize that with Crank-Nicholson. So we collide the lambda first. We've got a formula for it. And then I want to collide the magnetic field using the midpoint value, Crank-Nicholson. This U thing doesn't change, so it doesn't matter where I evaluate it. So I can solve. Nice property that lambda tensor at equilibrium, so the electric field, if you like, doesn't change, because if you work out this new thing, it's the same as the old thing. That's the first variant. So we keep momentum conservation, just muck about with the induction equation. But what Ken Powell did was to say, well, actually, I don't like that. I want my Lorentz force to be J cross B again. So then I need my Maxwell stress and a correction term, B dot grad B. So now I've got to have a right-hand side for colliding B and for colliding U. And then if I factorize my Crank-Nicholson, so I have these bits after and for, and I factorize this, this is a consistent factorization of what natural Crank-Nicholson, product at the end, product before, factorizes like this, and I have a nice solution. And again, the lambda tensor at equilibrium is unchanged. So then if I'm doing all this, I could think, well, maybe actually, I could just do the whole Lorentz force as a source term. And some of the early work on 3D lattice bolts and MHD did it this way too. So then now I've got to take out the Maxwell stress from there, put the whole Lorentz force in here using the current I get from the anti-symmetric parts of that non-equilibrium lambda, scale it, take it in the midpoint. This is my J twiddle thing. And then the kind of fun thing is that the exact solution for the Crank-Nicholson collisions is the Boris pusher that Patrick Jenny was talking about this morning that people use for particle and cell code. So this gives you an exact rotation of the velocity relative to a J cross B, so it's got nice stability properties. Okay, so now some numerical experiments. So original scheme, divergence of the Maxwell stress has a problem if we have this completely artificial field that's purely divergent. Just to test it, so the Lorentz force is identically zero, but this thing is not zero. So if we run it, what happens is we squeeze the fluid, and then we build up some gas, squeeze the fluid until the gas pressure is balancing the magnetic pressure, and then because we got some resistivity, the magnetic field will decay, and then it will start slumping back down again because the magnetic pressure decays too. Whereas if we do the variant with the B dot grad B source term, it looks qualitatively the same, but except we look up there, there's a factor of 10 to the minus 5. So compensating divergence of Maxwell stress with this correction term is not perfect, for the same reason that in multi-phase lattice bolts, when you have a pressure gradient and a density times a chemical potential gradient, they don't balance exactly because the product rule doesn't work exactly discretely, but it's pretty good. If you do the third variant with the J cross B all in the collisions, you just see zero here. Does nothing. Okay, more interesting benchmark. If we take a magnetic field of this form with F some function of polar radius, that's analytically always divergence-free, not divergence-free when we discretize it. So I'm going to plot some of that, and I'm going to diagnose Dsfd using this weird-looking finite difference formula, which is a linear combination of taking points on the axes to work out a divergence, points on the diagonals, and you can show that this is the thing that's most compatible with how the lattice-Boltzmann discrete stream collide works. So then plots initial current. It's a weak field because I wanted to just look at a kinematic problem. The divergence, it's got this weird multipolar pattern because what we're seeing here is the discretization error, which depends on the grid. And if I run the original lattice-Boltzmann scheme, this is a flow with a uniform flow just to affect the magnetic field, that the current just gets moved along by the flow, doesn't do anything. The field's so weak it exerts very little Lorentz force. Divergence just sits there and goes nowhere. I mean, that's the problem with standard Maxwell's equations. dt time derivative of divergence is zero. So if you create some by accident or by discretization error, It just sits there, it won't do anything. Whereas this new scheme, it gets advected by the fluid velocity, so this has moved along like the currents. And then if I do another benchmark, so this is taking smooth initial conditions with now getting the full Lorentz force from the collisions, and what I get for peak current, peak vorticity is exactly the same as the original lattice-Boltzmann scheme, putting the Lorentz force into the Maxwell stress, whereas here we're having to do the differentiation through the collision operator. I mean, I thought this was a crazy idea when people started doing it, but it just works just as well, and it's actually more stable. So that's just pictures, current and vorticity. We start off with something really, really smooth, and then we wind up to form intense currents and, okay, wrong plot there. Current and vorticity at later times. That was these things that are going up to a peak and back down again. Okay, I see Steam Chair is looking at his watch, so I better sum up. So Maxwell's equations, div B equals 0, typically gets broken numerically. Eight wave variance says we should advect those magnetic charges to restore Galilean invariance. We don't have to choose whether we want the Lorentz force J cross B or the divergence of the Maxwell stress. We can implement all of those. In particular, this one closely matches the standard scheme. So I think I'm not really seeing much in the way of accuracy here, but what is coming out is it seems the main benefit is stability, just like fixing up the cubic error term in the viscous stress. It doesn't need to help much with accuracy unless you have a very contrived benchmark, but it does help with stability. So thanks very much for your patience.
Try to solve the Riemann problem for this power system with your method.
Well, so my method is intrinsically resistive and diffusive, so I would have to do that variant. You can't do the ideal problem.
So it's too diffusive to have similarities with the true Riemann problem?
I haven't actually, to be honest, I haven't tried to see how close you could get it. That would be an interesting thing to look at. Yeah.
Stability, so is the chance to analyze the stability of
So at the moment, I'm just reporting observations. Yeah, so that thing is stable at 512 for those parameters, it's stable at 512 squared with this new scheme. With my original lattice-Boltzmann scheme, I need to go to 1024 squared. I haven't done any more than that at the moment. I suspect it's going to be one of these sort of horrible nonlinear things when we need to try and work out how to analyze.
Well, let's think more again.
Thank you.
Lunch is set up exactly the same.
Thanks.